Hello there, I'm Thomas Hatsios, the pilot captain flying the Boeing 777-300 ERX in tonight's flight from Zurich International Airport. We're going to be overflying takeoff from runway 14 at Zurich International Airport, overflying Zurich and Switzerland and Germany, and then coming back to Switzerland and Zurich Airport Lszh International, runway 14 for landing. So right now I'm in the cockpit for the pre-takeoff preparation of the Boeing 777-300 ERX of the PMDG simulations and Microsoft Flight Simulator X. So right now I'm gonna start showing you the instruments of the aircraft, like the displays, the primary flight display, that you can see the airspeed and the barometric altitude above the sea level, the radio altitude, the flight guidance, and the altitude of the aircraft, in the horizontal situation indicator of the HSI that displays the flight director crossbars and the pitch ladder and the bang angle in degrees of the aircraft in flight director mode, flying manually, or in autopilot mode, flying automatically. So we also have the vertical rate of climb and descent. We have the magnetic and true heading, magnetic north-south true north pole reference. So we also have the airspeed selected from the autopilot and flight director system panel, and the altitude selected from the autopilot and flight director system panel. We have the radio altitude above the ground level as a reference, and the barometric pressure of the atmosphere around the aircraft. So we also have the vertical rate of climb and descent of the aircraft in feet per minute, tape also in the primary flight display, and all this information is being provided by the ADIR, the Air Data Inertial Reference Unit, in the overhead panel that contains 3 or 2 GPS receivers. Also contains other information like other systems like the laser gyroscopic laser gyros for the gyroscopic acceleration and deceleration of the aircraft in horizontal and vertical altitude that displays the HSI altitude of the aircraft, and also for GPS positioning of the aircraft. So we also have the barometric altitude and the dynamic airspeed, the pitot barometric and the pitot dynamic cube that feed this information, this sensor. So we also have the angle of attack of the aircraft. I'm gonna show you now. We have here is the primary flight display. As I told you, contains the information, the airspeed, the ground speed, the minimum airspeed display is 30 knots. The barometric altitude above the sea level, 1,430 feet. Our airspeed right now actually is 0 knots. So we have magnetic and true north reference here, the radio altitude, the flight director crossbars over here in the primary flight display, the airspeed selected and the altitude selected from the autopilot flight director system, the takeoff go around mode. Here's the flight mode annunciator, the altitude selected from the autopilot flight director system, and the vertical rate of climb and descent tape, this tape over here. So you can see the barometric pressure, you can see the pitch ladder in degrees, the angle of attack of the aircraft, and the horizontal altitude, horizontal and vertical altitude. So you can see here we also have the navigation display. Also it's been supplied by the ADIR, the Air Data Inertial Reference Unit, or the Air Data Inertial Reference Unit, or the IRS. So it displays the GPS position, the terrain map using the radar of the aircraft, the weather radar that also reflects the ground. It displays this information in terrain levels with green, yellow, and red colors depending on the altitude around our aircraft or below. So we also have the airports, we have the waypoints, the voice stations, the ADF, magnetic true north, the wind direction and airspeed, and the next waypoint we're gonna be flying using our flight plan. We're gonna input a flight plan using the flight management computer. So you can see here is the navigation display, contains this information. I told you the ADIR is over here in the overhead panel. You can see the Air Data Inertial Reference Unit, that has the GPS controllers. GPS controllers are data information using static, barometric, gyroscopic acceleration, deceleration, laser gyroscopes, and also uh, airspeed, barometric altitude, radio altitude, magnetic compass through north magnetic. So this is being supplied by these streets over here. Very important for every aircraft airliner. So we have GPS positioning and other data in case we have no GPS available. So you can see here is the airports around us. Maybe I use this smaller range here. Some airports maybe not displayed so well, not so far away, I don't know why. So now we have all the airports here in this distance and the terrain scan from the radar, as you can see. So we align the IRS using this flight management computer and the ADIRU. You can see here the FMC position. You can do coming here in this view over here. And I'm showing you CDU1. So you go in the FMC, the model, the positioning using the reference airport is a good idea. Let's C8. So you have the reference airport over here, and you set the IRS, inertial IRS position. Set position. So now we have the IRS position using the flight management computer and the ADIRU over here, the air data inertial reference unit. Over here I'm gonna show you another view over here, the upper panel. So here we have another view of the cockpit, as you can see, of the Boeing 777 300 ERX, more panoramic view of this cockpit. So you can see the systems here. You can see the thrust levers. I'm gonna show you now what the autopilot, the displays. Here's the yoke, the control column, the rudder pedals. So you can see here is the ADIRU in the overhead panel. We start maybe with this, aligning the aircraft position. Here's the primary flight computers in the auto. The electrical panel, I'm gonna talk to you in a few minutes. The hydraulic panel over here. The window heats, cargo fire, the engines, electronic engine control computers, the auto start. The fuel system, the fuel jettison, the fuel tanks and the fuel pumps, left wing, right wing and center, fuel wing tanks and center tank and pumps. So this is a nice view of the overhead panel of the Boeing 777, the RDI system, the cabin pressurization system, automatic or manual. We have also the bleeder here from the engines, which is pressurized air from the engine's compressors, 5th and 9th stage, or the APU, for engine starting, for starting the engines in run, and also for the other systems. I will explain why the hydraulics here, the wing and engine are the ice in the cabin pressurization. So we have the electrical over here on this side for this aircraft, very important. The autopilot here, you can see the autopilot section. So it's the autopilot here, the auto throttle, engage and disengage. So we have the autopilot system also, the autopilot engage and disengage switches, the airspeed, we have also the airspeed select knob and display, and the modes of the auto thrust system, for climb continuous, for fly level change, for auto thrust, auto throttle hold switch, for the speed select. We have the autopilot connected and disengage, engage and disengage button and switch, and also the lateral and vertical navigation using flight management computer inputs for vertical and lateral navigation of the aircraft flying through waypoints, and also used for ILS approach. So also in the primary flight display we have using the flight director crossbars, we can use the ILS localizer, tuning automatically a frequency over here in the radio panel, radio navigation panel. We can tune the ILS localizer for approach. We have many radios, some are communication, some are navigation. So we have the ILS localizer displayed with the ILS localizer frequency, but it's tuned automatically using the flight management computer inputs, using our aircraft calculations for takeoff. We also use the departure runway and departure airport, and the arrival runway and airport and pictures for arrival for ILS localizer arrival. For instance, everything is tuned from the flight management computer. We only need to set up the autopilot panel. So we set up the panel like that. You can see we have also, besides the airspeed, select knob and guidance, select engage switches. We have the LNAV, VNAV, autopilot, engage, disengage, auto throttle, left and right, engage and disengage. Heading select, select the heading or the bang angle limit in flight for the autopilot and flight director, or flying heading manually. We also have the heading select knob and the heading hold switch. We have the vertical rate of climb and descent, the VS, or the flight path angle, FPA, using flight path angle of PA in degrees, in trigonometric degrees, or vertical speed VS in feet per minute, like hundreds or thousands of feet, or 2,000, 3,000 feet per minute, flying or descend the aircraft. We also have the altitude hold and the altitude select knob, the altitude hold switch, and the altitude that selects the barometric altitude the aircraft is gonna fly. So we have here the autopilot engage, disengage, flight director engage, disengage, auto throttle arm on and off, left and right. The airspeed select here. You can select a different airspeed like 250 knots will display here, and the airspeed select a different airspeed. So altitude also a different altitude, like we will select 1,000, 35,000. You can select 25,000, like 300, 400, or the altitude we're gonna be flying, using the auto over the 1,000 here. So you can see the displays, the airspeed knob here. You can depress it. Also we have the climb continuous, the auto thrust, flight level change, LNAV and VNAV, airspeed or Mach, knots or Mach, heading track. Here you can select a different heading, like the runway we're gonna use for takeoff. (137°), and the hold switch for the heading. So we can use also flight path vertical speed here. You can climb and descend in thousands of feet per minute here, minus 800 for instance, or plus 3,500. It will display here the VS, the vertical speed mode, or the flight path angle. So we have the minus or plus, descend or climb the aircraft. So you can see FPA here. You can use the FPA. It's magnetic through heading, the radar scanning the other aircraft flying around us, the terrain here, The level 6100, maximum 0 feet, minimum displayed with green, maximum with red, intermediate with yellow. And the distance right now is 160, 320, 320 nautical miles. Our heading is track is magnetic 325 degrees. So we can change around a couple of modes in the autopilot to show you the hold, heading hold, maybe a nav hold, I'm not sure. So now we have heading hold and nav hold. We select airspeed later if we want like flight level change. We also have the autopilot connect here. We cannot connect it like that. We have to select the maybe this is also depressible. The switch, all of them are depressible. Select through the selector mode. So we have also the vol localizer and the approach for Lszh localizer approach mode. Couple more buttons and switches here, so you can see flight director here is engaged. So now we can engage the autopilot here. I believe 137. Have to engage the altitude. It doesn't engage yet, so it's okay, we can do it later if we need. So we engage the autopilot using this switch, disengage it using this switch over here, or using this switch here in the in the control yoke here. We have switch for the stabilizer trim and also for the autopilot disconnect, or by moving our yoke using some abrupt movement. So we also have over here the auto throttle disconnect switch here for the thrust levers. We also have flight director on and off, auto throttle left and right on and off, some systems on and off. So we use the hold now here, hold, maybe use heading, still not be able. So it's okay, we can use it later. So not losing too much time with the autopilot section. So we have a few more minutes to go. You can see the cockpit of the Boeing 777 here. I'm showing you. You can see the yoke, you can see the tiller, the rudder pedals, these flight control surfaces. Maybe I'm gonna show you the engines first, what they do. So maybe I'm gonna show you the thrust levers. I use the thrust levers to adjust the thrust of the aircraft as we have to move in the runway for takeoff, after starting the engines, or as we fly, produce enough airspeed to produce aerodynamic lift to fly the aircraft. So you can see here, if we produce enough aerodynamic lift from the engines, airspeed achieved, because we accelerate the aircraft using the thrust by the differential pressure between the forward and the aft section of the turbofan turbojet engine, from the suction and the ejection of the compressed air and the hot gases. So this accelerates the aircraft forward if we need it. So you can see also here we have the flap levers, which are additional secondary flight controls. We can move the flaps down to increase the surface area of the wings. This makes the weight of the aircraft, using the flaps makes the weight of the aircraft being proportional to a higher wing surface, which makes the wing loading, the weight of the aircraft over the surface area of the wings less this ratio using some physics. I'm gonna talk to you about some physics now, some Newton physics and some mathematics. So this makes the aircraft having less wing loading and make it easier. It makes the stall speed less, so you can fly with lesser speed or take off more easily using less runway. If we use the proportional flaps and flaps for takeoff, as you can see here, the flaps and flaps expanded. The surface is over here. So you can see also the flappers we use for flying the aircraft, the spoilers. So this produces aerodynamic lift and some airflow mass deflection when the aircraft is flying. To create so aerodynamic lift and airflow mass deflection using the surfaces of the flight control to make the aircraft change its altitude in flight, like pitch up or pitch down or bank or left and right. So we use this to pitch up and pitch down the aircraft, the yoke of the airplane, the control column for pitching up and pitch down, and the control wheel for bank or left and right for ailerons and spoilers. So you can see here we have certain inertial position, a couple more things, manual for cycle displays. So we have synoptics, the flight controls. You can see the flight controls here in this display. The ailerons, the spoilers, the flappers. You can see the engines of the aircraft here. So this is all the flight control surfaces, the horizontal stabilizer here, and the rudder. So we have the stabilizer and the rudder trim. We need some Newton's physics and some mathematics to make aerodynamics and aerospace engineering. Also for aircraft performance for flying, having ATPL ATPL. It also needs some aerodynamics and some flight performance. ATPL is the air transport ATPL transfer pilot license. So it's for airliner flying aircraft, for like the Boeing 777 or the 737. So you can see we pitch up and pitch down the aircraft using the horizontal stabilizer elevator section. So we use also the pitch trim of the horizontal stabilizer, which balances the aircraft using its aerodynamic forces from the tail, the horizontal tail of the aircraft as we fly. So you can see here pitch up and pitch down using the elevator and bank roll using the ailerons and the spoilers. So you can see here I'm using this side stick to input all the altitude needed for flying the aircraft. After I achieve an airspeed like 150 knots or 250 kilometers an hour in the runway for takeoff or for landing. After that we're airborne, we have an airspeed above the stall speed using some flaps. So I use this stick to fly the aircraft to maintain its flight altitude. So pitching up, pitching down, bank roll left, bank roll left, bank roll right, and also rudder pedals left and rudder pedals right. So pitch up, pitch down, bank roll left, bank roll right, pitch down, pitch up, and rudder pedals left, rudder pedals right. We also have the horizontal stabilizer of the aircraft for pitching up and pitching down the tail of the aircraft to balance the aircraft in flight. And we have the thrust levers here, and we also have the speed brakes. We have the landing gear extender retract over here. So we have also the flaps, as I said, to increase the lift. So the main principle is after we achieve an effective airspeed in the runway like 250 kilometers an hour or 150 knots and higher, depending on the weight of the aircraft and other factors like the length of the runway, that we use the barometric pressure and the temperature of the air. So we can achieve an airspeed above the stall speed for the wings. We can start pitching up the aircraft for takeoff. We do the rest after flying, pitching up and pitching down or banging on left and right. The stick or the yoke over here. So you can see the proportional inputs from my hand using the stick, or is transferred using computer into the control yoke of the aircraft over here, of the Boeing 777-300 aircraft. Pitch up, pitch down, bunker, left and right, and also the rudder pedals for directional control. So after you achieve an effective airspeed, you achieve an effective aerodynamic lift that counteracts the gravity and the weight of the aircraft to lift the aircraft in the air, using its wings, its forward wings lift, having more airspeed in the air mass above the wing and less airspeed in the air mass below the wing. We have a differential pressure, more pressure below the wing and less pressure above the wing, makes differential pressure above and below. The wing that makes the aircraft flying. We have lift above the wing and more air pressure below the wing, higher pressure. So you need to remember this when flying. A couple more things to note about this: the aerodynamic lift using the forward wings. We have the aerodynamic lift using the wing. We have the mean aerodynamic chord position with the center of pressure. We have a position with maximum aerodynamic lift in the wing. We have the center of gravity of the aircraft, which is located above, which is located forward for us. The max, the mean aerodynamic chord of the forward wing, that the center of aerodynamic pressure has been created. So the aircraft pitches up and pitches down using the vertical axis that transverses this position of the center of gravity and the center of aerodynamic pressure. Okay, thanks. So this creates the aerodynamic lift, and after that we have this center of gravity and center of aerodynamic pressure. We transfer all the moment arms for directional control using the side stick here, as I said, using the elevator pitch up and pitch down that is located in a distance away from the center of aerodynamic lift and the center of gravity of the aircraft, that the weight is being located. Then makes the aircraft pitch up like this, using the tail, the horizontal tail, to create a moment arm around its axis. So you use some Newton's physics, some mathematics. So you know the moment arm using some trigonometry, some sinus angles, some cosinus angles, some trigonometric tangent angles, sinus angles, cosinus angles, theta angles. As the aircraft is flying for bank roll, using differential lift between the left and right wing also creates a G load that makes the aircraft turn in one direction, either way left or right. We have more lift in one way, the left or the right. Using the ailerons and the spoilers, we can turn the aircraft like that, other way. We can turn the aircraft left, right. We can pitch up and pitch down. We have the moment arm, and some trigonometric angles, some mathematics, some G loads, some G acceleration from the gravity, and the forward thrust from the engines must be equal or higher than the drag from the air friction and the spin of the aircraft. So this is the theory. The lift overrides the lift of the aircraft wings, overrides the weight of the aircraft. So we also have directional control using the rudder, left and right, around the same principle. As you can see, bungle left, bungle right, using differential lift between the left and right wing. More lift in one wing, less lift in the other. Makes the aircraft turn in the other direction. There is less lift actually. So the same for pitching up and pitching down. So you can see here, this is the principle for the flight controls: pitch up, pitch down, bungle left and right. So I'm gonna show you now inside the aircraft. This is, I believe, enough for these flight controls lesson. So you can see again how we fly the aircraft. Pitch up, pitch down, bungle left and right, directional control using the rudder pedals, and the thrust from the engines. Adjust the thrust from the engine. So we have like 30 more minutes, I believe, for this flight. 30 or 40 minutes. So I need to show you the cockpit very quickly. I hope you understand this principle of the flight control. I will show you the cockpit now. The rest of the instrument, the ACAS, the upper ACAS, and the lower ACAS. I display the engines, permanent information, sound system inside the cockpit, and make the engine start demonstration instead of the flight management computer, flight plan, and flight path. So I come here again. I'll show you have the flight controls here, the captain and the first officer in the other side. So we have I'm gonna show you the thrust from the engines. So you can see the systems here displayed in the lower ACAS. We have the modes, we have the status here. You can see the APU, the auxiliary power unit, is off. So we come over here in the overhead upper panel. You can see again the autopilot here. We have you come here, starter switch, the APU, the auxiliary power unit, in the start. You can see the start here is the left engine and the right engine electrical power. So we have for this aircraft 150 volts 400 Hz or 200 volts 400 Hz frequency, constant frequency, three-phase alternate current from the left engine, and the same from the right engine, because when the engines are working and produce thrust, they also move out the gearbox that contains electromagnetic brushless electromagnetic alternators, bipolar, north pole and south pole, that create electromagnetic induction alternate current that feed the aircraft, supplies the aircraft with alternate current. For this needs about 120,000 actually kilovolts or 120,000 watts each engine, left engine, right engine, 140,000 kilovolts or 240,000 watts in total. We have additional backup generators, 25,000 kilovolts each one, 150 to 200 volts, 400 Hz frequency, and 4 wire each one. We have the connector, the contactors from the bus ties, contactors, the RDT, the great drive generators, contactors here. You can see you can connect and disconnect. If you, maybe we have the APU ready now. If the APU is running, so I will show you here. Yes, it's running fully right now, 100%. So we can show you this over here. This display the electrical, overhead lower, overhead upper. So you can see if we disconnect this, we still have the APU now and the batteries to supply the aircraft. So we can use the alternate current. You can see electrical generator of right, of left, and the backup system, the electric here. The fuel pump is no fuel in the center fuel tank, so we have to reconnect these switches here. We have also the batteries here, the APU battery, so we can convert the alternate current from the generators, from the electromagnetic generators, into directly using transformer rectifiers, using some electrical engineering. So we also can convert the battery current, which is constant and no alternating. It's direct current 38 volts, 7 ampere hours. We can convert it into alternate using static inverters. We can also here in the overhead panel, we have something like the hydraulics here. Left engine, right engine. Connect and disconnect. We disconnect now the hydraulic system. So we have the flaps primary fail. This is the hydraulic pumps from the engine. When the engines work, also produce hydraulic power using some hydraulic pumps. You can see all the flight controls now fail. We have alternate landing gear and flaps and slats, alternate flaps. So if I come here in this display, you will see the synoptics, the hydraulics here is off. The hydraulic system is isolated, we have no PSI. So if I come here in the overhead panel and fix this hydraulic system, we have some failures. We have also the flight controls also fail. You can see the flight controls, no flight controls now. We have the system, the hydraulic, left, right, C, left and right engine and the backup. So there is no flaps, no slot, no rudder, no directional controls here. So we have the electrical here, is normal, the hydraulics is gone. So overhead upper panel, we come over here, we reconnect the hydraulic pumps, 3000 psi when we turn them on, all primary and backup. We have the left and the right engine and the backups here, the electrical design pumps. So we have the ram air turbine also, in case we lose all the systems, to extend in the air smaller turbine. So use some other systems now, a couple more systems. So we have this is now the hydraulics fully working and powering up flight controls. So using all this here, the control column and the control wheel, we need the hydraulic power from this system to move the flight controls in the air. So also the rudder pedals, we need the hydraulic power to move the rudder. All surfaces are electrically actuated by electrically controlled but hydraulic actuated. So this is electrical left and right engine, 115 volts, 400 Hz frequency, alternate current, the APU generator, the backup generators, the direct current battery. So you can see the bus tie contactors. This is the system I showed you in the overhead panel. So we have the engines are fully working right now. The status, the APU can start the engines using the APU, the auxiliary power unit. So we have the checklist here, the normal before takeoff, for instance. This is what we need to do for flying the aircraft, or having some failure, like engine failure, for instance, and we need to do some research. So this is the complete non-normal menu here. You can see engines and fire protection. So engines and APU here, damage, failed, shutdown thrust. So we have the engine failure and what we need to do. Engine failure, right? For instance, you can see no, only one engine, for instance. So this is the steps we need to do. Restart is needed, yes. Monitor, engine may accelerate. So this is what we need to do if we have an engine failure. Slow acceleration, maybe as long restart, airspeed is above. Fuel control run. So this is all the system. Both engines run normally, yes. Plan to run, running using flaps steady, yes. So this is the menu for this. We have also the communications, the air traffic control, also the synoptics, the electrical, hydraulics, fuel, left and right engine, also now in the overhead panel. So we have overhead upper panel, we have the left and the right engine auto start system. and the electronic engine control computers for the engines that control the FADEX, the full authority and digital electronic control computers. You see the start position now. We have the auto start on and off. The normal, we can dump fuel in flight jettison. We have the fuel jettison from the fuel tanks, and also arm this. We have the left and the right wing and the center and the crossfeed for balancing between the left and right wing, or using only one side, tank or pump, to feed either engine. You can see the thrust levers here. We'll monitor in a while. We also have here the air system. We have the cabin pressurization, automatic and manual pressurization here. We have the controllers for climbing and descending the aircraft by opening and closing the outflow valves for climbing, for pressurizing the aircraft when climbing, or to pressurize in descent. If we have the manual mode right now, if we have automatic, we leave the computers controller. Then we have the increase, decrease the altitude. Here we have some wipers, we have some lights, the wing and engine RDI system, the lighting of the aircraft, the wiper for the wing, the windshield, actually not the wing. So we have the auxiliary power unit here, the left and the right engine. This is the bleed air, compressed bleed air, that is being used for the cabin pressurization and also for the hydraulic fluid pressurization, for the engine start pressurization. We have the packs left and right that admit the pressurized air here. I will show you the system now. So I will come here in the CDU. So you can see the fuel system. This is the air system. The left and the right engine, the pressurized air. When the engine is working, also produce compressed air for the flight controls, for the fluid, for the hydraulic fluid, and also for cabin pressurization, and also for air conditioning, and for wing and engine RDI. So you can see if we increase here the thrust from the engine, if we move the thrust levers forward, you will see the duct pressure over here increase. You see duct pressure 40, 49, 50. So this increased the air produced from the engine that has been bleed out or admitted from the 5th and the 9th stage of the turbofan or turbojet engine of this airplane. So we have the isolation valves, we have the APU. We can use, when the engine starts, we have to use the APU to pressurize the engine starter. This pressurizer, because turbofan engine. We use also this for air conditioning, for when the engine got the ice, using the packs here. I'll show you the packs flow. So you can see the temperature here inside the aircraft. Here is the fuel system, the left and right wing engine, the APU, the engine. You can see the engine symbol here that is being fed, and the low and high pressure fuel valves are open. The crossfeed valves are open to feed either wing tank using one pump only. If we turn off the pumps, we have also the APU feed using the right current pump here, and the left and center tank is empty. The tank 1 and tank 2, we can see the minimum fuel temperature minus 37 degrees when we fly. You can see the engine symbols and the total fuel for this aircraft. The Boeing 777 ERX is right now 30% or 46,600 kilograms. So this is most of the system. We also have the flight controls that I saw you already. You can see that moving the rudder pedal here. Moves the rudder. So the speed brakes extend here. You will see the speed brakes extending. We have the door are closed and pressurizing the aircraft cabin. The gear is down, and you can see the pressure inside the tires and the temperature of the brakes. So we have also, as I told you, the engines. We're gonna go in the engines now more deeply. So you can see here is the fuel system, as I told you, the pressurizer. So we have the engines here moving forward. Increases the thrust, as you can see. We have the N1, which is the low speed, low pressure compressor stage of the engine, with the engine thrust. I will tell you about that. The exhaust gas temperature, the duct pressure, coming altitude and rate for the outflow valves, the flaps position, some warnings, the fuel quantity here, the total fuel and the temperature. So you can see the N2 also, the speed brakes, the stabilizer trim, the normal and alternate cutout stabilizer trim, the parking brakes. So you have everything. You have the fire extinguishers and the fuel flow. Uh, the fuel flow for stopping or restarting the engines. We have also the flaps position here. I'm gonna use it position 15 for this takeoff. For this, so we have the flight management computer, communication panel here. You see the displays also. Over here, this view, nice view of the aircraft. So we're gonna make an engine start demonstration. You can see the autopilot is set for takeoff. So this is the thrust from the engine, this and this. Gonna come now here. Hope not forget anything. So I'm coming in this view. We have a few more minutes to go. Like 30 more minutes to go. So here is the thrust produced from the engines. If I increase the thrust levers, you will see the forward thrust. The N1, which is the low speed, low pressure compression stage of the engine, you can see the symbol of the thrust levers position is different from the actual thrust until the thrust is balanced. The exhaust gas temperature, left and right, the cabin pressurization, total fuel, flaps position. I'm gonna use flaps 15, not 5. Landing gear here is down. Landing gear normal, alternate, and auto brake system. You can see here flap override, and you can have the N2, which is the high pressure, high speed rotor stage of the turbofan turbocharged engine. The fuel flow per engine per hour 4,100 right now, 3,500. Oil pressure, oil temperature, oil quantity, and the vibration of the engine. So we also have the reverse thrust here, which extends also the speed brake during landing. So we use the reverse. You can see the reverse as N1 symbol is being displayed, and this slows down the aircraft after landing. So here we are. We have a couple more minutes to start the engine. So you can see the reverse here is being engaged. We close the reverse. We don't need reverse right now. So you will see now we'll turn off the engine. Now the engines are working. I will come inside and show you maybe I will turn off both fuel flow levers here. So you can see the N1 is going down, it's slowing its rotation right now. Engines are down, display select. So everything is slowing down here for this aircraft, you know. The fuel flow is 0. These are not fuel flow, DFS. So you can see also the spinners have started spinning. The aircraft, the Boeing 777 airplane, turbofans here, turbofan. You can see are slowing down now. So they're gonna come in a stop. You can see here no spinning. We go now inside. We turn on the left wing first. Auto start system. We have the dome on. All the lights are on. Summary configuration. So we're gonna see the N1 here increase first. Very slowly, 2.7. The exhaust gas temperature only 173. So now we have hot pressurized air from the APU admitted. The N2 is above 20%. The fuel flow is 0. So you can see now the left wing engine. The right wing engine is off. The left wing engine starts spinning. So we go inside. You can see the left wing engine is spinning. Fuel flow is 0. So we admit fuel now into the turbo fan. engine. The Rolls-Royce RB11. So this is the fuel flow increase very rapidly. 43% fuel flow 0.7. So we have the spinner here ready to start giving spin into the engine. So we go now in the other side engine. The right wing is off. You see no spinning. So we come here in the overhead panel, start the spinner, the right wing auto start system that controls the FedEx full authority digital electronic control computers that control and display on the information you see here, control and monitor the engine's function, the turbofan engine's function and gearbox function. We have also the fuel flow controls and monitors the limits and the thrust levers or the auto throttle. So it's all controlled by FedEx. We have the end two increases. You can see the spinner here. We have started having some spinning for starting the engine. So we start the fuel flow is 0. Fuel control levers here. And to increases, fuel flow is 0, 0.2, 0.4. So we start the engine process. Give the aircraft this starting engine start. So we're ready and configured for takeoff. We only need one last final step. You can see the transponder here and the TCAS, the traffic collision alert system, for displaying our position and receiving other aircraft position and altitude. The DSB transponder. So we have the menu, FMC, we have the position index, initial reference, so 0 fuel weight and plus the fuel, 235,000 kilograms. The fuel is 46,300. The reserve fuel is 5%. The cost index, the flight altitude is 25,100 set from the autopilot panel. The cost index 100. A minimum fuel temperature and cruising center of gravity. We have the route from this airport Lszh into this departure destination, runway 14. Activate. So we need first to use departure runway. You will see the flight plan being created in a while. Select this one, runway 14. This airport departure and this departure fix. So departure arrival ILS 14 for the same airport, and trans this Negro 1 Alpha, trans Hamiki, execute, enable cruise altitude. So we have no active route because we need to cancel this discontinuity. Execute again. So we have the takeoff reference now. The takeoff center of gravity 36%. The trim position, as I told you, for the horizontal tail is gonna be 4 degrees for balancing the aircraft around its mean aerodynamic chord. So it's CG 36% of mean aerodynamic chord, 4 degrees up. So V1 133, V rotating 140, V2 154, gross weight 234,000. So we're ready for takeoff and flying like 30 more minutes. Just taxi into the runway. So here we are. We have to taxi into the runway. Advance some thrust levers here. Disarm the parking brakes and use the tiller here. This tiller to move the forward wheel, the nose wheel steering. So we have directional control in the ground using the tiller and the rudder pedals for the nose wheel. We have to fly the aircraft for about 20 minutes, so advance the thrust levers again. So we use the parking brakes set, the flight director primary flight display, we use this, and the LNAV, later on navigation, the runway heading for takeoff. So we're gonna have the Lszh localizer here. You can see the flight path we're gonna fly now, and the radio altitude, the barometric altitude, the airspeed is gonna be attained by the aircraft after we move the thrust levers forward. So we have control, and we have like maybe 5 and 23 minutes for this flight. As you can see where we are right now in this airport. So we can start now. You can see everything the display. So you can see the autopilot is set. We move the thrust levers forward to balance the thrust over here, the takeoff thrust. The N1 is increasing. You can see the thrust lever limit here for takeoff has to be about this green needle, about 103%. So we disarm the parking brakes and go. So we use maximum takeoff thrust for this runway. So you can see the airspeed here increases. We have V1, V rotate. Use some directional control. So here we go. We have positive rate of climb. Retract the landing gear. We decrease a little bit the thrust after takeoff. So we control the aircraft using the control wheel now. We leave it pitched up. So our altitude above the ground level, you can see the radio altitude is 2,480, 2,500 feet, and it's gone. Our airspeed 250 knots. You can see the ground level here, the terrain scan from the radar. You can see our altitude, barometric 5,600 feet above the sea level, rate of climb 6,000 feet per minute. So we need to trim down the stabilizer a little bit, no pitch up so much. As we're making this turn, you can see the stall speed also here display, the modes. So here we are after takeoff, climbing out. So this is the climb out for this airplane, the Boeing 777. 300 VRX. We have about 30 minutes left for flying. 25 minutes left. So this is the runway over here. You can see Zurich and the lakes, the beautiful lakes. So we keep traveling the climb out. So you a little bit more inside as we're climbing out. The climb out with maximum pitch altitude right now and maximum thrust over here. I'm trying to pitch up again. You can see we need to retract the flaps now a little bit higher to increase the thrust limit. So this warning need to cancel. We have a little bit of overspeed right now. So it's gonna cancel on its own if we increase the rate of climb. So this was for the autopilot actually. So we disconnect the autopilot again, connect and disconnect to cancel this warning. So you can see now the max speed is 0.411 or about 500 kilometers an hour or 150 maybe 200 meters per second air speed. It's gonna be about 300 later meters per second. So right now it's about 500 kilometers an hour is about 200 meters per second or 200 knots. So the rate of climb 2600 altitude. You can see the waypoints now we're gonna be flying through. This intersection. Τώρα περίμενε. So we keep climbing out. You can see this is our spacecraft for tonight, the Boeing 777-300ERX. You can see this beautiful star sign here. (30,000 feet) crossing the Alps here region. The Swiss Alps, we have Germany in front of us, the Bavarian Alps and the Bayern Munich region. This is Switzerland, this is Germany over here. So you can see our airplane, the Boeing 777-300ERX flying with about 500 kilometers an hour right now, 30,000 feet or 6,000 meters above the sea level. Hope you like its views. These beautiful views of the Boeing 777-300ERX aircraft. So now we have the chemtrails. We are 23,000 feet above the sea level. We keep climbing. 32,000. So having got a little bit more minutes to fly. 32,000. You can see the stall speed here. We have like about 15 minutes to go. We have like 12 minutes left to go for this flight. So you can see the star sign here. So we keep climbing up. We almost reached our altitude for flying. A couple more minutes. 34,700. You can see the story. Our max speed right now is Mach 0.549. So here we are. It pitched down the aircraft. 35,300 feet. We try to balance and then turn back into the airport. So we balance like this. Also use maybe flight level change here. So we have now the auto thrust controlling the thrust of the engine to balance the aircraft a little bit as we fly. So we need to retract the flaps a little bit further. We have the engine exhaust. Produce less airspeed. So we can see here now we're flying 35,000 feet, 35,300 feet with about Mach 0.5 or 600 kilometers an hour or 250 meters a second. So you can see here is our spacecraft for tonight. This is the beautiful views of Switzerland, overflying the lake, with Germany, the Bayern Munich region in front of us. So we need to go back in a while, start going back into our airport. So this is Germany here. So we increase the max speed here and make a turn into the airport. Turn into the airport, back into the airport. Flying manually here. So we take the turn manually, having higher airspeed, and also retract the flaps here. We don't need so many flaps, so this is gonna give us higher airspeed. So you can see here we have the stall speed we need to avoid while we increase the airspeed while we're taking this turn. You can turn more, a little bit more bang angle. Trying to pitch down to 35,000. So we cross the Germany here. Here we are, overflying Switzerland and Germany. 35,000 feet right now, 300 meters a second, 900 kilometers, 950 kilometers an hour. So here we are. We have this beautiful view of the Boeing 777. We have like 10 minutes left to go, 10 or 12 minutes. So we cross here. As you can see, we have the frozen vapors here now. We have the galaxies here view. This is the Boeing 777, 950 kilometers an hour. 6,000 meters above the Earth level, flying closer to the troposphere, so fast, close to the Mach speed. Hope you like our airplane, the Boeing 777-300, flying so fast, 950 kilometers an hour, or Mach 0.78, Mach speed 0.78. So we go back into our airport right now. We need to connect the autopilot now for balancing the flight a little bit. And flying direct into the last waypoint of the flight. So the last waypoint is gonna be this. The motive, the execute, connect and execute this line, flying direct into so we're flying now directly into the airport. We have like a few more minutes left to go for this flight, so we need to go faster now for landing. Increase the simulation rate a little bit maybe. So keep it flying 950 kilometers an hour, this high altitude, 6,000 meters above Germany and Switzerland. We love Germany and Switzerland, it's true. We are just 46 nautical miles away from the Lszh, so we need to start descent now. Decrease maybe the airspeed a little bit and select the lower altitude. Here in the autopilot we will select the lower altitude for flying. We are just 37 nautical miles away, so we will start descent now. Flight level change here, mode, and press this altitude switch here. So you will see the descent start immediately. Mach 0.78, 950 kilometers an hour. We have a few more minutes to go. You can see the thrust now is decreasing automatically to the idle. We have an idle position for approach and landing. We have a few more minutes left to go actually. So we need to make a very fast approach and landing. Use a simulation acceleration mode here. And also select here initial reference flaps 35 degrees flaps and slots. Keep descending 31,000 feet. Flying with maximum airspeed right now, not slowing down the aircraft. We keep flying with about 800 kilometers an hour right now, above 5,800 maybe meters above the earth right now. So this is nice view here. "15 nautical miles away, decrease maybe the airspeed a little bit. So making a safer approach into the runway. As we get closer, we need also to slow down a little bit as we're coming closer into the runway. Mach 0.62. You can see the rate of descent 2,000, 3,000 feet per minute. Select the VS, the vertical speed. Disengage the autopilot now and fly manually a little bit. So we go down to the approach, extend the landing gear now. We need to slow down and have the landing gear in position so you can see the runway this way. You have to use the approach mode, so we have to slow down the aircraft a little bit. Down its approach speed for landing. 163 knots right now. We have the overspeed now. So here we are, very close. It's getting night now, so you can see we have the landing gear down here. You can see as we get closer into the runway, we need like a couple more minutes to get down into the runway. So maybe like 2 or 3 minutes left for this flight. We need to use some flaps also. So the runway is this side. This is how we get closer into the runway. Closer and closer. We have like 3 minutes left to go. Overspeed the aircraft a little bit. Flying manually, we're gonna have the Lszh localizer now. You can see where we are right now, our aircraft position. We're very closer into the ground, closer into the runway, and the clouds also. So use more flaps now for slowing down the aircraft as we approach into the runway. We need like a couple more minutes to go. We are limited by video time, unfortunately. I hope we're gonna make it. A couple more minutes. Just landing into the runway very fast. No time to explain everything. We have an Lszh localizer here. Approach. So disengage the autopilot here. We'll cancel the warning. We don't need the autopilot right now.